The universe creates explosions that make our sun look like a dying match. Most people think supernovas are the ultimate cosmic blast. They're completely wrong. Tonight we're discovering what actually creates the universe's most violent eruptions, and why these cosmic monsters can briefly outshine entire galaxies. Before we dive into these stellar catastrophes, drop a comment about where you're listening from. If you enjoy these cosmic mysteries, consider subscribing. These explorations of extreme physics are meant to be shared. Military satellites hunting for nuclear weapons found something impossible instead. Strange flashes of invisible light from deep space. Scientists call this invisible light gamma rays, the most powerful form of energy that exists. These weren't coming from anywhere nearby. The flashes originated from distances so vast that their light had traveled for billions of years to reach us. And they were still bright enough to blind our most sensitive detectors. What astronomers discovered shattered every assumption about how stars die. Each burst lasted mere seconds. Yet during those few heartbeats, these explosions outshone every star in entire galaxies combined. We'd found the universe's ultimate expression of raw power. Our sun has been shining steadily for 5 billion years. It will keep burning for another 5 billion years before running out of fuel. These cosmic explosions release that same total energy in just a few seconds. Picture the ultimate energy converter. Take an entire planet and transform completely into pure light. That's the energy scale these bursts achieve in moments. The physics becomes completely extreme. Matter shoots through space at nearly the speed of light itself. Temperatures climb higher than anything else in the universe. Magnetic fields millions of times stronger than Earth's twist space into impossible shapes. Nature reserves these explosions for its most catastrophic stellar deaths. Only the most massive stars can create such concentrated fury when they collapse. These explosions don't spray energy in all directions like normal stars. Instead, they create something like cosmic searchlights. The energy gets squeezed into narrow beams that slice through space in specific directions. Picture a lighthouse beam spinning across a dark ocean. But this lighthouse beam travels at nearly the speed of light and carries enough energy to vaporize entire solar systems. Most of these cosmic lighthouses point away from Earth. We only detect the rare ones whose beams happen to sweep across our planet. This means the universe creates far more of these explosions than we can actually observe. The beam structure explains why these bursts appear so incredibly bright. All that devastating energy gets focused into a narrow cone instead of spreading out weakly in all directions. When these explosions ignite, they create temperatures beyond human imagination. The heat climbs to billions of degrees. That's thousands of times hotter than the core of our sun. At these extreme temperatures, normal matter simply can't exist anymore. Atoms get ripped apart completely. Even the particles inside atoms break down into their most basic components. Scientists call this state of matter plasma, a soup of particles so energized they move at incredible speeds. This isn't the gentle plasma you might see in a lab. This is plasma pushed to the absolute limits of what physics allows. The temperatures are so extreme that they bend the rules of space and time themselves. Matter and energy become interchangeable. The boundary between particles and pure energy starts to dissolve. These bursts don't all last the same amount of time. Some flash for just milliseconds. Others continue for several minutes. This timing difference reveals something crucial about how they form. Scientists have discovered that short bursts and long bursts come from completely different cosmic disasters. It's like finding out that lightning and earthquakes both make loud noises, but for totally different reasons. Short bursts typically last less than 2 seconds. Long bursts can continue for hundreds of seconds. The timing acts like a cosmic fingerprint that tells us which type of stellar death we're witnessing. This discovery revolutionized our understanding of stellar evolution. The universe has multiple ways to create these ultimate explosions, each leaving its own distinctive signature in time. These explosions happen so far away that their distances challenge human comprehension. A light year measures how far light travels in 1 year. These bursts come from billions of light years away. To put that in perspective, light from these explosions began traveling toward Earth before our planet even had complex life. The light has been racing through space longer than multicellular organisms have existed. Despite these mind-boggling distances, our instruments can still detect them clearly. This tells us something remarkable about their true power. An explosion visible from billions of light years away must release almost unimaginable energy. The vast distances also reveal that these events happen throughout the entire observable universe. Every galaxy appears capable of producing these cosmic catastrophes under the right conditions. When astronomers mapped where these bursts appear in the sky, they found something surprising. The explosions don't cluster around our galaxy's center or along its spiral arms. Instead, they appear randomly scattered across the entire sky. This random distribution provided crucial evidence that these events happen far outside our own galaxy. If they occurred within the Milky Way, we'd see them concentrated along the band of stars visible in our night sky. The uniform distribution across all directions tells us we're observing a phenomenon that affects the entire universe. Every region of space, in every direction we look, occasionally produces these cosmic explosions. This discovery transformed our understanding of the cosmic scale. We realized we were witnessing events occurring in distant galaxies billions of light years away. During their peak intensity, these bursts become the brightest objects in the universe. A typical galaxy contains hundreds of billions of stars. A single gamma-ray burst can outshine that entire stellar collection. Gamma rays represent the most energetic form of light that exists. They carry far more punch than visible light, X-rays, or radio waves. When these bursts peak, they become gamma-ray blazes visible across the entire universe. The brightness levels reach hundreds of times greater than entire galaxies. Picture every star you can see in the night sky suddenly blazing hundreds of times brighter simultaneously. That barely approaches the intensity these cosmic monsters achieve. This extreme brightness allows us to study stellar death processes occurring in the most distant reaches of space. We can observe the final moments of massive stars that died when the universe was young. The matter in these explosions moves so fast that Einstein's relativity effects become extreme. Particles accelerate to speeds approaching light itself. At these velocities, strange physics phenomena take over. Time dilation means time itself flows differently for the high-speed matter. Length contraction squeezes distances in the direction of motion. Mass and energy become interchangeable through Einstein's famous equation. These relativistic effects amplify the brightness we observe. Matter moving toward us at near light speeds creates a focusing effect called relativistic beaming. This concentrates the energy and makes the explosions appear even more brilliant. The physics becomes so extreme that space and time themselves get distorted around these cosmic catastrophes. We're witnessing stellar death under the most extreme conditions possible in our universe. In our entire galaxy, these ultimate explosions happen incredibly rarely. Scientists estimate one occurs roughly every few tens of thousands of years. That's rarer than mass extinction events on Earth. During all of recorded human history, our galaxy has probably produced 0 of these cosmic catastrophes. The last one in the Milky Way likely occurred before human civilization began. This rarity makes each detected burst scientifically precious. We're witnessing stellar death events so extreme that most galaxies go millennia between occurrences. Each observation provides a rare glimpse into the universe's most violent processes. The scarcity also explains why these explosions remained hidden until recent decades. Only advanced space-based detectors could finally reveal these cosmic secrets that happen so rarely and so far away. If one of these cosmic monsters occurred nearby, it could threaten all life on our planet. The gamma-ray radiation would strike Earth's atmosphere and trigger a devastating chemical reaction. The high-energy radiation would destroy ozone molecules that protect us from the sun's harmful ultraviolet light. Without this protective ozone layer, deadly UV radiation would reach Earth's surface at lethal levels. Scientists estimate that a gamma-ray burst within a few thousand light-years could cause a mass extinction event. The increased UV radiation would damage DNA, kill plants, and collapse food chains from the bottom up. Fortunately, these events occur so rarely and so far away that Earth has likely never experienced a nearby gamma-ray burst throughout its entire history. We exist in a cosmic safe zone that has protected life for billions of years. Cold War paranoia led to an unexpected cosmic breakthrough. American military satellites called Vela were launched to spy on Soviet nuclear tests. These detectors were designed to catch the gamma-ray signature of atomic bombs anywhere on Earth. Instead, they caught something completely different. The satellites detected gamma-ray flashes that clearly weren't coming from Earth. The signals arrived from random directions in space with no pattern that matched any human weapons testing. Military scientists faced a puzzling dilemma. Their nuclear monitoring system was picking up explosions far more powerful than any bomb humans had ever built. And these mysterious blasts were coming from somewhere in the depths of space. The discovery remained classified for years, while scientists struggled to understand what their spy satellites had actually found. They'd stumbled upon the universe's most violent phenomena while hunting for earthly weapons. What if the most important astronomical discovery of the century was locked away in military files? For years after the first detections, this cosmic mystery remained hidden behind Cold War secrecy. Only government scientists with security clearances could study the data. The end of the Cold War changed everything. Military authorities finally declassified the Vela satellite observations. When civilian astronomers first saw the data, they realized they were looking at something completely unprecedented. Decades of accumulated observations suddenly became available to the global scientific community. The military had been quietly documenting cosmic explosions, while the astronomy world remained completely unaware of their existence. This declassification opened floodgates for research. Scientists could finally study patterns in the mysterious signals and begin developing theories about their cosmic origins. How do you pinpoint an explosion that lasts only seconds and comes from somewhere in the vast cosmos? Scientists developed a clever solution using multiple satellites spread across the solar system. When a gamma-ray burst occurs, it reaches different satellites at slightly different times. Light travels incredibly fast, but the distances between satellites are large enough to create measurable time delays. By comparing these tiny timing differences, scientists could triangulate the burst's direction. It's like using cosmic triangulation to map explosions happening billions of miles away. This technique revealed that bursts came from all directions, randomly scattered across the sky. The universe was producing these mysterious explosions everywhere, not just in specific cosmic neighborhoods. The Compton Gamma Ray Observatory carried an instrument called BTSE into orbit specifically to hunt for these cosmic explosions. BTSE stands for Burst and Transient Source Experiment. This detector revolutionized our understanding by collecting systematic data. Over 9 years of operation, BTSE detected thousands of gamma-ray bursts. Each detection provided crucial clues about duration, intensity, and sky location. Scientists finally had enough data to identify patterns. The systematic observations revealed that bursts fell into distinct categories. Some lasted milliseconds while others continued for minutes. This timing difference suggested completely different types of cosmic catastrophes were creating the explosions. BTSE transformed gamma-ray burst research from scattered observations into rigorous science. The large dataset allowed scientists to test theories about what might cause these cosmic monsters. If gamma-ray bursts came from our own galaxy, they would cluster along the Milky Way's band of stars. Scientists expected to see more bursts in some directions than others. What they found completely contradicted this expectation. The bursts appeared uniformly distributed across the entire sky. No matter which direction astronomers looked, they found roughly the same number of explosions. This uniform distribution is called isotropic by scientists. This discovery provided crucial evidence about distance. Objects within our galaxy would show clustering patterns. Only phenomena occurring at vast cosmic distances would appear uniformly distributed from our perspective. The uniform sky distribution proved that these explosions originated in distant galaxies scattered throughout the universe. We were witnessing cosmic catastrophes occurring billions of light years away. For nearly 30 years, astronomers fought bitterly over a fundamental question about gamma-ray bursts. Were these explosions happening relatively nearby within our galaxy, or were they occurring at unimaginable distances in other galaxies? Two competing theories emerged with passionate supporters on both sides. The local camp argued that bursts came from special stars in our cosmic neighborhood. The cosmological camp insisted they originated from distant galaxies billions of light years away. The stakes were enormous for understanding stellar physics. If bursts were local, they represented relatively modest stellar explosions. If cosmological, they required the most extreme energy releases in the known universe. Scientific conferences became battlegrounds as researchers presented contradictory evidence. The debate highlighted how little we understood about these mysterious cosmic events and the distances involved. An Italian-Dutch satellite called BeppoSat solved the distance debate with a technological breakthrough. Unlike previous detectors, BeppoSat could rapidly locate gamma-ray bursts and immediately observe the same sky region with X-ray telescopes. Within hours of detecting a gamma-ray burst, BeppoSat would spot a fading X-ray source at the exact same location. This X-ray afterglow provided the precise coordinates needed for follow-up observations with other telescopes. For the first time, astronomers could point optical telescopes at the exact spot where a gamma-ray burst had occurred. This capability transformed burst astronomy from passive detection to active investigation. BEPISAX observations finally settled the distance debate. The precise locations allowed astronomers to identify the host galaxies where these explosions occurred, proving their cosmological origin. Gamma-ray bursts don't simply flash and disappear forever. Scientists discovered that the explosion sites continue glowing for weeks or months afterward in other types of light. This extended emission is called the afterglow. The afterglow starts bright and gradually fades over time. Initially visible in X-rays, it eventually becomes detectable in optical light and radio waves. Each wavelength reveals different physics from the explosion's aftermath. These afterglows provided the missing link needed to study burst environments. While the initial gamma-ray flash lasts only seconds, the afterglow gives astronomers time to examine the explosion site with multiple telescopes. The afterglow discovery revolutionized gamma-ray burst science. Scientists could finally study the stellar neighborhoods where these cosmic catastrophes occur and begin understanding their physical mechanisms. The Hubble Space Telescope made the distance measurements that stunned the astronomy community. By analyzing light from gamma-ray burst host galaxies, astronomers could determine exactly how far away these explosions occurred. Scientists measure cosmic distances using redshift. As light travels through the expanding universe, it gets stretched to longer, redder wavelengths. The amount of redshift reveals how long the light has been traveling. Some gamma-ray bursts showed redshifts corresponding to distances of over 10 billion light-years. This means we're observing explosions that occurred when the universe was less than half its current age. These extreme distances confirmed the cosmological nature of gamma-ray bursts and revealed their incredible energy output. Explosions visible from such vast distances must release almost unimaginable power. Modern gamma-ray burst research requires telescopes that observe different types of light working together in perfect coordination. When a burst occurs, observatories worldwide spring into action within minutes. The observation network spans from gamma-ray satellites to radio telescopes on Earth. Each telescope type reveals different aspects of the explosion physics. Gamma rays show the initial blast, rays track the early afterglow, and optical telescopes study the host galaxy. Rapid communication systems alert astronomers worldwide when a burst occurs. Telescopes automatically point toward the burst location to capture the rapidly fading afterglow before it disappears. This coordinated approach has revolutionized our understanding of cosmic explosions. Scientists can now study gamma-ray bursts across the entire electromagnetic spectrum and piece together the complete physics of stellar death. Scientists noticed something strange when they plotted the lengths of thousands of gamma-ray bursts. The data showed a clear gap around 2 seconds. Almost no bursts lasted exactly 2 seconds. Instead, the explosions fell into 2 distinct groups. Short bursts ended in less than 2 seconds. Long bursts continued for tens of seconds or even minutes. This clean separation puzzled astronomers for years. The 2-second boundary acts like a cosmic dividing line. It separates gamma-ray bursts as clearly as different species of animals. Scientists realized they were actually observing 2 completely different types of stellar catastrophes. This duration difference became the key to unlocking the mystery of how these cosmic explosions form. The timing reveals which type of stellar death created each burst. Long gamma-ray bursts prefer certain types of cosmic neighborhoods. These extended explosions typically occur in galaxies that are actively forming new stars. Scientists call these star-forming galaxies because they contain the raw materials needed to build fresh stellar generations. These lengthy bursts can continue for several minutes after their initial flash. During this extended period, they release enormous amounts of energy across multiple wavelengths of light. Astronomers discovered that long bursts cluster in specific galactic regions. They favor the spiral arms where massive young stars congregate. This location preference provided crucial clues about which types of stars create these extended explosions. The connection between long bursts and star formation suggests that only recently formed massive stars can produce these extended cosmic catastrophes. Short gamma-ray bursts tell a completely different cosmic story. These brief flashes prefer older, quieter galactic neighborhoods. They frequently occur in elliptical galaxies that stopped forming new stars billions of years ago. The contrast couldn't be more striking. While long bursts come from cosmic nurseries bustling with stellar birth, short bursts emerge from galactic retirement communities filled with ancient stars. These quick explosions last less than 2 seconds but pack incredible punch into their brief duration. Despite their short timescale, they can still outshine entire galaxies during their peak intensity. The preference for old stellar populations suggests that short bursts result from the deaths of stars that formed when the universe was much younger. Gamma-ray bursts don't maintain the same color throughout their explosions. Scientists observe a phenomenon called hard-to-soft evolution. This means the gamma rays start at higher energies and gradually shift to lower energies over time. Think of this like a firework that starts brilliant white and fades through yellow to red. But instead of visible colors, gamma-ray bursts shift through different energy levels of invisible light. The two types of bursts show distinctly different color evolution patterns. Long bursts display more complex spectral changes over their extended duration. Short bursts show simpler patterns that match their brief timescales. These spectral differences act like fingerprints that help scientists distinguish between the two types of cosmic explosions and understand their underlying physics. Long and short gamma-ray bursts choose completely different cosmic real estate. Long bursts concentrate along spiral galaxy arms, where massive stars are born and live brief, violent lives. Short bursts scatter more randomly throughout their host galaxies. They appear both in galactic centers and outer suburbs. This scattered distribution matches the wandering paths of old stellar populations. The location preferences make perfect sense when you consider stellar lifetimes. Massive stars that create long bursts never travel far from their birthplaces before dying. Older stellar systems that create short bursts have had billions of years to migrate throughout their galaxies. This galactic geography provides strong evidence that different types of stars with vastly different lifespans create the two burst categories. The most massive stars in the universe create long gamma-ray bursts. These stellar giants contain dozens of times more material than our Sun. Their enormous mass determines both their explosive deaths and the type of burst they produce. Short bursts come from much smaller stellar remnants. These explosions involve stars that originally contained only a few times our Sun's mass. By the time they create gamma-ray bursts, they've already shed most of their outer material. The mass difference explains why the two burst types behave so differently. Massive stars have the fuel needed for extended explosions. Smaller stellar systems produce quick, intense flashes when they finally meet their cosmic end. This mass explosion connection reveals that stellar size fundamentally determines which type of gamma-ray burst will result from stellar death. Long gamma-ray bursts show a strong preference for chemically simple stellar environments. Scientists measure stellar chemistry using metallicity. This term describes how much of a star contains elements heavier than hydrogen and helium. Stars with low metallicity formed from relatively pure hydrogen and helium gas. Stars with high metallicity contain significant amounts of carbon, oxygen, iron, and other heavy elements that previous stellar generations created. Long bursts occur preferentially in low metallicity environments. This chemical preference suggests that only stars formed from relatively pristine gas can create these extended cosmic explosions. The metallicity connection helps explain why long gamma-ray bursts were more common in the early universe when heavy elements were scarce. Some long gamma-ray bursts have cosmic companions. Astronomers discovered that certain long bursts occur at exactly the same time and place as specific types of stellar explosions called supernovas. These paired events involve type IC supernovas. This category represents stars that have lost their outer hydrogen and helium layers before exploding. The naked stellar cores detonate in particularly violent fashion. The timing and location matches prove that some massive stars create both phenomena simultaneously. The supernova represents the star's outer material exploding outward. The gamma-ray burst represents jets of material shooting from the collapsing core. This partnership reveals that gamma-ray bursts and supernovas can be two aspects of the same catastrophic stellar death process. Short gamma-ray bursts sometimes produce unusual infrared afterglows that fade over several days. Scientists call these glowing remnants kilonovas. The name refers to explosions roughly 1,000 times brighter than ordinary stellar explosions called novas. These infrared glows have a distinctive reddish color that reveals something remarkable about their composition. The light comes from newly created heavy elements like gold, platinum, and uranium cooling and condensing in space. Kilonovas provide direct evidence that short gamma-ray bursts create and distribute precious metals throughout the universe. The infrared glow represents cosmic alchemy in action as stellar material transforms into the heaviest elements. This connection explains where many of the heavy elements in our universe originally formed before being incorporated into planets and life. In 2017, scientists achieved a breakthrough that solved the mystery of short gamma-ray bursts. They detected gravitational waves and a gamma-ray burst from the same cosmic event simultaneously. Gravitational waves are ripples in space and time itself created when massive objects accelerate. These ripples travel at light speed and can be detected by incredibly sensitive instruments on Earth. The combined detection showed that short gamma-ray bursts result from neutron-star collisions. When two ultra-dense stellar remnants spiral into each other, they create both gravitational waves and gamma-ray emission. This discovery provided definitive proof that short bursts originate from the mergers of compact stellar objects rather than single massive star explosions. Long gamma-ray bursts generally pack more total energy than their shorter cousins. The extended duration allows these explosions to release energy over longer periods and reach higher total outputs. However, short bursts can achieve comparable peak power during their brief moments of maximum intensity. They concentrate enormous energy into very short timescales, creating incredibly intense but brief cosmic flashes. The energy difference reflects the different mechanisms creating each burst type. Massive single stars collapsing into black holes can sustain energy output longer than neutron-star mergers. Both types rank among the most powerful explosions in the universe, but long bursts typically claim the title for total energy release. The rate of long gamma-ray bursts throughout cosmic history closely follows the universe's star formation activity. During epochs when galaxies were rapidly creating new stars, long bursts occurred more frequently. This correlation makes perfect sense given what we know about long burst origins. Since massive stars create these explosions, their rate should track the formation of massive stars throughout cosmic time. The universe's star formation peaked several billion years ago when galaxies were younger and contained more raw material for building stars. Long gamma-ray burst rates peak during this same cosmic epoch. This evolutionary connection provides strong evidence that long bursts serve as cosmic tracers of massive star formation across the history of the universe. Only the most extreme stellar deaths can produce long gamma-ray bursts. Scientists call this process the collapsar model. The term describes what happens when a massive rotating star collapses directly into a black hole. Most stars die relatively quietly. They puff off their outer layers or explode as ordinary supernovas. But the most massive stars undergo something far more catastrophic. Picture a stellar giant spinning rapidly as it runs out of nuclear fuel. Instead of stopping at the neutron-star stage, gravity crushes the core beyond all known limits. The collapse continues until it forms a black hole. This direct collapse to a black hole distinguishes collapsar events from ordinary stellar explosions. Only this extreme process can generate the focused energy beams that create gamma-ray bursts. Deep inside massive stars, nuclear fusion creates increasingly heavy elements throughout the star's lifetime. Hydrogen fuses into helium. Helium fuses into carbon. The process continues building heavier and heavier elements in the stellar core. Eventually, fusion creates iron, but iron nuclei cannot fuse to release energy. Instead, iron fusion actually consumes energy. When the core fills with iron, the star's nuclear furnace shuts down completely. Without fusion energy pushing outward, the iron core becomes unstable. Gravity suddenly gains the upper hand against all the forces that had kept the star stable for millions of years. The iron core marks the point of no return for massive stars. Once fusion stops, catastrophic collapse becomes inevitable within seconds. As the iron core collapses under gravity, a fundamental physics principle takes control. Angular momentum must be conserved. This means the total amount of spin in the system cannot change. Think of an ice skater pulling in their arms during a spin. As the skater's mass moves closer to the rotation axis, they spin faster and faster. The same physics governs collapsing stellar cores. The stellar core shrinks from thousands of kilometers across to just tens of kilometers. This dramatic size reduction causes the rotation rate to increase by enormous factors. A core that initially rotated once per day might end up spinning hundreds of times per second. This extreme rotation becomes crucial for launching the jets that create gamma-ray bursts. The collapsing stellar core encounters increasingly desperate resistance from matter itself. First, atomic structure breaks down under the crushing gravity. Then even atomic nuclei get squeezed into neutron soup. Neutron degeneracy pressure represents one of the strongest forces in physics. This quantum mechanical effect normally stops stellar collapse and creates neutron stars. But the most massive cores overwhelm even this ultimate resistance. When gravity defeats neutron degeneracy pressure, nothing in the known universe can stop further collapse. The core shrinks past the critical radius where space and time themselves break down. An event horizon forms around the collapsing matter. This invisible boundary marks the point where gravity becomes so strong that nothing, not even light, can escape. The rapidly rotating material around the newly formed black hole cannot fall straight inward. Instead, it settles into a flattened disk structure. Scientists call this an accretion disk. The disk material orbits the black hole at tremendous speeds while gradually spiraling inward. Friction between different parts of the disk generates incredible heat. Temperatures climb to billions of degrees. This isn't a solid disk like a music record. It's a swirling maelstrom of superheated gas and plasma. The material glows intensely from the extreme temperatures generated by gravitational compression. The accretion disk becomes the fuel source that powers the gamma-ray burst. Energy extracted from the disk's rotation and gravitational infall drives the entire explosive process. The rotating plasma in the accretion disk acts like a giant electromagnetic dynamo. Charged particles moving in circles create magnetic fields. The faster the rotation, the stronger these fields become. The magnetic field lines get twisted and amplified by the disk's differential rotation. Different parts of the disk rotate at different speeds, wrapping the magnetic field into increasingly tight spirals. This process amplifies relatively weak initial magnetic fields by factors of millions or billions. The result is a magnetic field structure more powerful than anything else in the known universe. These amplified magnetic fields become the cosmic machinery that launches material away from the black hole at nearly the speed of light. The twisted magnetic field lines create something like cosmic rail guns pointed along the black hole's rotation axis. Magnetic pressure builds up tremendous force that can accelerate matter to extraordinary speeds. Material gets funneled along the magnetic field lines and shot outward in narrow beams. These jets travel at speeds approaching the speed of light itself. Scientists call this relativistic motion. The magnetic acceleration is so powerful that it overcomes the black hole's enormous gravity. Material that would normally fall inward instead gets ejected at incredible velocities. This jet formation represents one of the most efficient energy conversion processes in the universe. Gravitational and magnetic energy transforms into kinetic energy of high-speed matter. The high-speed jets must blast their way through the star's outer layers to escape into space. These outer layers, called the stellar envelope, contain most of the star's mass. Picture a cosmic drill boring through thousands of kilometers of stellar material. The jets create shock waves as they punch through the dense outer layers. Most of the stellar envelope gets blown away by these shock waves. Only the fastest, most focused jets successfully break through to open space. Weaker jets get trapped inside the star and never produce gamma-ray bursts. The breakthrough process takes just seconds but determines whether the stellar death produces a gamma-ray burst or merely an ordinary supernova explosion. Once the jets escape the stellar envelope, they create the gamma-ray emission we observe from Earth. Internal shock waves within the jets produce most of the high-energy radiation. The jets aren't perfectly uniform. Faster-moving sections catch up with slower sections and create collision zones. These internal shock waves heat the jet material to extreme temperatures. At these temperatures, the shocked material radiates gamma rays. These represent the most energetic form of electromagnetic radiation. Each gamma-ray photon carries far more energy than visible light or X-rays. The gamma-ray production happens in the first few seconds after the jets break free. This explains why gamma-ray bursts flash so briefly despite the enormous energies involved. Not every massive star collapse creates a gamma-ray burst. Sometimes the jets fail to break through the stellar envelope. When this happens, the result is a more ordinary type of stellar explosion. If the jets remain trapped inside the star, their energy gets distributed throughout the stellar material. Instead of focused beams, the energy creates a roughly spherical explosion. This produces what astronomers call a core collapse supernova. The star explodes and creates heavy elements, but no gamma-ray burst emerges. The explosion lacks the focused energy necessary for burst production. Failed jet scenarios may actually be more common than successful ones. This explains why gamma-ray bursts are much rarer than ordinary supernova explosions. Creating a gamma-ray burst requires very specific stellar conditions. The star must be both extremely massive and rotating rapidly. It also needs to have relatively low amounts of heavy elements. Stars with high metallicity lose mass through stellar winds throughout their lifetimes. This mass loss removes both material and angular momentum. By the time such stars reach core collapse, they no longer rotate fast enough to form jets. Low metallicity stars retain more of their original mass and rotation. These conditions existed more commonly in the early universe when heavy elements were scarce. The combination of high mass, rapid rotation, and low metallicity creates the perfect recipe for gamma-ray burst formation. Without all three ingredients, massive star death produces ordinary explosions instead. Two neutron stars locked in cosmic dance face an inevitable fate. These ultra-dense stellar remnants orbit each other in ever-tightening circles. Einstein's theory predicts they must lose energy by creating ripples in space itself. Gravitational waves carry away orbital energy with each revolution. Think of it like cosmic friction that can't be stopped. The neutron stars spiral closer together over millions of years. As the orbit shrinks, the orbital speed increases dramatically. The neutron stars begin racing around each other hundreds of times per second. Their final plunge takes just minutes from the point where gravitational wave detectors can sense their approach. This death spiral represents one of the universe's most precise clocks. Scientists can predict the merger time down to fractions of seconds once the final phase begins. Neutron stars contain matter crushed to an imaginable density. A teaspoon of neutron star material would weigh as much as a mountain. Yet even this incredibly dense matter gets torn apart by tidal forces during the final merger. Tidal forces occur when gravity pulls harder on one side of an object than the other. Near the merger, these forces become strong enough to overcome the neutron degeneracy pressure that holds neutron stars together. The tidal disruption creates streams of neutron-rich matter flying away from the collision site. This material carries the raw ingredients needed to build the heaviest elements in the periodic table. Without tidal disruption, neutron star mergers would simply create larger neutron stars or black holes without ejecting the material necessary for heavy element formation. The ejected neutron star material creates conditions impossible to achieve anywhere else in the universe. Scientists call this environment perfect for rapid neutron capture. The R in our process stands for rapid. Imagine an atomic assembly line running at impossible speed. Iron nuclei get bombarded by neutrons so fast they don't have time to decay between captures. Each iron nucleus absorbs dozens of neutrons in seconds. Normal stellar processes can't build elements heavier than iron efficiently. They lack both the neutron density and the rapid timescale needed. Only neutron star mergers provide the extreme conditions for rapid heavy element production. This cosmic alchemy transforms abundant, lighter elements into rare, heavy ones like gold, platinum, and uranium. The entire process completes within seconds of the merger. The newly created heavy elements don't remain stable after formation. Many of these freshly forged nuclei are radioactive. Their decay provides the energy source for a distinctive type of cosmic lighthouse. Scientists call this glowing aftermath a kilonova. The name indicates an explosion about 1,000 times brighter than ordinary stellar explosions called nova. But kilonovas glow with a distinctive reddish color. The red color comes from the specific heavy elements created during neutron-star mergers. As these radioactive elements decay, they release energy that heats the expanding debris cloud. This heated material glows like cosmic embers. Kilonovas fade gradually over several weeks as the radioactive fuel gets consumed. This extended glow allows astronomers time to study the heavy element production process in detail. Neutron stars possess the strongest magnetic fields in the known universe. These fields can be trillions of times stronger than Earth's magnetic field. During merger, these powerful magnetic fields get twisted and tangled in extreme ways. The twisting process stores enormous amounts of magnetic energy. Eventually, the twisted field lines snap and reconnect in more stable configurations. This magnetic reconnection releases vast amounts of stored energy almost instantaneously. Picture cosmic rubber bands stretched to their breaking point and suddenly snapping back. The energy release accelerates particles to incredible speeds and contributes to the gamma-ray emission. Magnetic reconnection helps explain how neutron-star mergers can produce gamma-ray bursts despite their brief duration. The stored magnetic energy provides an additional power source beyond gravitational collapse. After neutron stars merge, the outcome depends on their combined mass. If the total exceeds a critical threshold, the merged object immediately collapses into a black hole. Scientists call this threshold the maximum neutron star mass. Neutron degeneracy pressure can only support so much weight. Beyond approximately twice our Sun's mass, no known force can prevent gravitational collapse. The merger remnant crosses this point of no return within milliseconds. Different neutron star pairs produce different outcomes. Lighter pairs might create massive neutron stars called magnetars. Heavier pairs inevitably form black holes surrounded by debris disks. The mass threshold determines whether the merger produces a long-lived neutron star or a rapidly forming black hole. This outcome affects both the duration and intensity of associated gamma-ray emission. When neutron star mergers create black holes, the surrounding debris doesn't disappear quietly. Instead, it forms a hot, rotating disk around the new black hole. This accretion disk becomes a launching pad for relativistic jets. The mechanism resembles what happens during massive star collapse, but with important differences. Neutron star merger debris contains more neutrons and fewer heavy elements than stellar material. Strong magnetic fields threading through the accretion disk help focus material into narrow beams. These jets accelerate to speeds approaching light and produce the gamma-ray emission we detect. The jet formation process must happen quickly since neutron star mergers don't provide sustained energy input like stellar collapse. This explains why short gamma-ray bursts last only seconds rather than minutes. Einstein predicted that accelerating masses would create ripples in the fabric of space and time itself. Neutron star mergers represent the perfect laboratory for testing this prediction with incredible precision. The gravitational wave signal from merging neutron stars has a distinctive pattern called a chirp. The frequency increases rapidly as the neutron stars spiral closer together, like a cosmic siren rising in pitch. Advanced detectors on Earth can sense these space-time ripples from billions of light-years away. The gravitational waves arrive at Earth traveling at light speed, often seconds before any electromagnetic signals. This timing difference allows astronomers to prepare telescopes to observe the merger aftermath. Gravitational waves provide early warning that a cosmic collision has occurred. Every gold ring and platinum catalyst on Earth contains atoms forged in neutron-star collisions billions of years ago. These cosmic mining operations scatter newly created heavy elements throughout space to be incorporated into future planets. The universe had no gold, platinum, or uranium when it first formed. These elements could only be created after neutron stars formed and had time to find each other. Early galaxies contained mainly hydrogen and helium. Neutron star mergers inject heavy elements into interstellar space where they mix with gas that will form future stars and planets. This cosmic recycling process gradually enriches galaxies with increasingly diverse chemistry. Without neutron star mergers, rocky planets like Earth would lack the heavy elements necessary for complex chemistry and technological civilization. Neutron star mergers happen far less frequently than other cosmic catastrophes. A typical galaxy experiences a neutron star merger roughly once every 10,000 years. This makes them much rarer than the massive star collapses that create long gamma-ray bursts. The rarity stems from the complex evolutionary path required to create merger candidates. Two massive stars must form close together. Both must explode as supernovas without disrupting their orbit, and the resulting neutron stars must spiral together over cosmic time. Each step in this process eliminates most potential merger candidates. The vast majority of binary star systems never complete the full sequence needed to produce neutron star collisions. This extreme rarity makes each detected merger scientifically invaluable. Every observation provides crucial data about heavy element production and gravitational wave physics that might not be repeated for years. Ordinary physics cannot explain how gamma-ray burst jets reach such incredible speeds. These cosmic bullets travel at more than 99% the speed of light. No conventional rocket or explosion can achieve such velocities. The secret lies in magnetic pressure working like a cosmic railgun. Twisted magnetic field lines store enormous amounts of energy around black holes and neutron stars. When these field lines snap and realign, they release stored energy almost instantaneously. The magnetic acceleration process operates more efficiently than any human-made propulsion system. It can convert gravitational and rotational energy directly into the kinetic energy of high-speed particles. This magnetic launching mechanism explains how relatively small stellar remnants can create jets that outperform the most powerful cosmic explosions. The focused magnetic pressure concentrates available energy into narrow beams rather than spreading it in all directions. Matter moving at nearly light speed creates an optical illusion that dramatically amplifies the brightness we observe. Scientists call this effect relativistic beaming. It transforms relatively modest energy outputs into the universe's brightest phenomena. Imagine a flashlight beam that gets squeezed into an increasingly narrow cone as you move faster. At normal speeds, light spreads out evenly in all directions. But at relativistic speeds, most of the light gets focused into a tight beam pointing forward. This beaming effect can increase apparent brightness by factors of hundreds or thousands. Jets that might appear ordinary when viewed from the side become cosmic monsters when viewed head-on. Relativistic beaming explains why gamma-ray bursts appear so incredibly bright despite originating from distant galaxies. We're seeing cosmic flashlights pointed directly at Earth with their light artificially concentrated by extreme physics. Einstein's relativity predicts that time itself behaves strangely for matter moving at near light speeds. Scientists measure this effect using the Lorentz factor. This number describes how much relativistic effects distort normal physics. For gamma-ray burst jets, Lorentz factors can reach several hundred. This means that 1 second experience by the jet material corresponds to hundreds of seconds as measured by distant observers. The extreme time dilation affects everything about how we observe these cosmic phenomena. Events that happen rapidly in the jet's reference frame appear stretched out when viewed from Earth. Length contraction works alongside time dilation to compress distances in the direction of motion. These combined effects create the exotic physics environment where gamma-ray bursts operate and help explain their unique observational properties. Gamma-ray burst jets aren't perfectly uniform streams of material. They consist of multiple sections moving at slightly different speeds. Faster sections inevitably catch up with slower ones ahead of them. When these internal collisions occur, they create shock waves within the jet itself. Picture cosmic traffic accidents happening at nearly light speed. The collisions convert kinetic energy into heat and electromagnetic radiation. These internal shocks produce most of the gamma-ray emission we detect from Earth. The shock heating accelerates electrons to extreme energies and creates the conditions necessary for high-energy photon production. Internal shock formation explains why gamma-ray bursts show complex, variable light curves rather than smooth emission. Each collision event within the jet creates a separate pulse of gamma-ray radiation. High-speed jets cannot travel through space indefinitely without encountering obstacles. Eventually, they slam into material that exists between stars. This collision creates a different type of shock wave called an external shock. External shocks form at the boundary where fast-moving jet material meets stationary interstellar gas. The collision heats both materials and creates a hot, compressed region that radiates intensely across multiple wavelengths. Unlike internal shocks that occur within the jet itself, external shocks represent the jet's interaction with its environment. This interaction gradually slows down the jet and changes its emission properties. External shock formation marks the transition from the brief gamma-ray phase to the longer-lasting afterglow phase. The physics shifts from internal jet dynamics to jet environment interaction. Gamma-ray burst jets aren't simple cylinders of uniform material. They have complex internal structure with different speeds and densities at different locations. The fastest material typically occupies the central axis. Think of a cosmic water jet where the center stream moves faster than the outer spray. The jet core travels at the highest speeds while material near the edges moves more slowly. This structured geometry affects how the emission appears to observers at different viewing angles. Only observers aligned with the fastest central core see the full gamma-ray burst. Others might see weaker emission or no burst at all. Jet structure helps explain why gamma-ray bursts appear to point preferentially toward Earth. We're not seeing all cosmic explosions, only the ones whose fastest cores happen to be aimed in our direction. Shock waves in gamma-ray burst jets act like cosmic particle accelerators more powerful than any human-built machine. The shock fronts can accelerate electrons and protons to energies millions of times higher than achieved in laboratory settings. The acceleration mechanism works through repeated encounters with magnetic fields embedded in the shock wave. Particles bounce back and forth across the shock front, gaining energy with each crossing. This process, called diffusive shock acceleration, can boost particles from ordinary thermal energies to relativistic speeds in remarkably short times. The most energetic particles achieve speeds within tiny fractions of light speed. The accelerated particles provide the energy source for most electromagnetic emission from gamma-ray bursts. Without efficient particle acceleration, these cosmic explosions would remain invisible across most wavelengths. High-energy electrons accelerated by shock waves don't simply fly through space in straight lines. They encounter magnetic fields that force them into spiral trajectories. This spiraling motion produces a specific type of radiation called synchrotron emission. Picture electrons following corkscrew paths around invisible magnetic field lines. As the electrons spiral, they radiate electromagnetic energy at wavelengths determined by their speed and the magnetic field strength. Synchrotron radiation typically produces X-rays and visible light in gamma-ray burst afterglows. The exact wavelengths depend on how fast the electrons are moving and how strong the magnetic fields are. This emission mechanism explains the smooth, continuous afterglow spectra observed across many wavelengths. Synchrotron radiation naturally produces the broad spectral features seen in most gamma-ray burst observations. High-energy electrons can do more than just radiate their own light. They can also boost the energy of existing photons through a process called inverse Compton scattering. This mechanism helps explain how gamma-ray bursts achieve their extreme high-energy emission. When a fast-moving electron collides with a low-energy photon, it can transfer some of its kinetic energy to the photon. The photon emerges from the collision with much higher energy than it started with. This energy transfer process can convert ordinary visible light photons into X-rays or gamma rays. The amount of energy boost depends on how fast the electrons are moving when the collisions occur. Inverse Compton scattering provides an additional pathway for creating the highest energy gamma rays observed in burst spectra. It works alongside synchrotron radiation to produce the full range of electromagnetic emission. Observers viewing gamma-ray bursts from different angles see distinctly different light evolution patterns. When the viewing angle exceeds the jet's opening angle, the afterglow brightness drops more rapidly than expected. This angular effect creates a characteristic feature in afterglow light curves called a jet break. The break appears as a steeper decline in brightness that occurs days to weeks after the initial burst. Before the jet break, observers see emission from the entire visible jet. After the break, relativistic beaming effects reduce the apparent brightness because the jet has slowed down enough that beaming no longer points directly at Earth. Jet breaks provide crucial information about burst geometry and total energy output. By measuring when breaks occur, scientists can determine how narrow the jets are and how much energy they actually contain. Gamma-ray burst jets don't naturally form as narrow beams. They require active collimation mechanisms to focus energy into the tight cones we observe. Magnetic forces provide the primary focusing system. Magnetic field lines threading through the jet material exert inward pressure that prevents the jet from spreading out. This magnetic hoop stress works like invisible walls that keep the high-speed material confined. External pressure from surrounding material also helps collimate jets. Gas and radiation pressure around black holes and neutron stars can squeeze jets into narrower configurations than they would achieve naturally. The collimation process must be highly efficient to create the narrow jets inferred from observations. Without strong focusing mechanisms, the available energy would spread over much larger solid angles and produce much weaker emission. Gamma-ray bursts don't simply flash and vanish forever. After the initial explosion fades, a completely different type of light show begins. This extended glow appears in X-rays, visible light, and radio waves simultaneously. Scientists call this extended emission the afterglow. Unlike the brief gamma-ray flash that lasts seconds, afterglows can persist for weeks or months. They provide a cosmic lighthouse that astronomers can study with multiple telescopes. The afterglow spans the entire electromagnetic spectrum. Each type of light reveals different physics from the explosion's aftermath. X-rays show the hottest material. Visible light reveals the cooling process. Radio waves track the slowest moving debris. This multi-wavelength emission allows scientists to piece together the complete story of what happens after cosmic explosions. Without afterglows, gamma-ray bursts would remain brief mysteries impossible to study in detail. The relativistic jets from gamma-ray bursts don't travel through empty space. They slam into material that exists between stars. Scientists call this sparse material the interstellar medium. When jets moving at nearly light speed hit this material, they create powerful shock waves. Think of it like a cosmic snowplow pushing through cosmic snow. The collision heats both the jet material and the interstellar matter to extreme temperatures. The shock waves gradually slow down the jets as they sweep up more and more material. This deceleration process changes how the emission appears to observers on Earth. The physics shifts from relativistic to more ordinary as the jets lose speed. This external shock mechanism explains why afterglows fade gradually rather than disappearing instantly. The collision process releases energy over extended periods as jets interact with their environment. Afterglow brightness doesn't decrease randomly over time. Instead, it follows precise mathematical patterns called power laws. These patterns allow scientists to predict how quickly afterglows will fade. A power law means the brightness decreases by a specific factor for each doubling of time. If an afterglow dims by half in one day, it will dim by another half in the next day, and so on. This creates a smooth, predictable decline. Different wavelengths of light follow slightly different power law slopes. X-ray afterglows might fade faster than optical afterglows. Radio afterglows often fade most slowly of all. The power law behavior reveals fundamental physics about how shock waves work and how they accelerate particles. Scientists can extract detailed information about explosion geometry from these mathematical patterns. Afterglows don't reach maximum brightness simultaneously across all wavelengths. Instead, they follow a predictable sequence. High-energy radiation peaks first, followed by lower-energy light in orderly succession. X-rays typically reach maximum brightness within hours of the initial burst. Optical light peaks a day or two later. Radio emission often doesn't peak until weeks after the initial explosion. This wavelength progression occurs because different energies of light come from electrons with different speeds. The fastest electrons radiate X-rays first. Slower electrons produce visible and radio light later. Scientists can use this timing sequence to map out the energy distribution of particles in the shock wave. Each wavelength provides a snapshot of different particle populations. The main afterglow emission comes from shock waves that move forward into the interstellar medium. As the jets push through space, they create a compression zone ahead of the moving material. This forward shock heats interstellar material to millions of degrees. The heated material radiates intensely across multiple wavelengths. Most of the afterglow light that reaches Earth originates from this forward-moving shock front. The forward shock also accelerates electrons and protons to extremely high energies. These accelerated particles spiral around magnetic field lines and produce the characteristic afterglow radiation. The forward shock mechanism dominates afterglow production because it encounters fresh, unshocked material continuously. This provides a steady source of energy for the extended emission. Not all shock waves travel forward through space. Some move backward through the decelerating jet material itself. Scientists call these reverse shocks because they propagate in the opposite direction. Reverse shocks form when fast-moving jet material encounters resistance from the external medium. The interaction creates a compression wave that travels back through the jet at high speed. These backward-traveling shocks often produce brief, bright flashes of optical light during the first few minutes after the gamma-ray burst. This early optical emission can sometimes outshine the later forward shock afterglow. Reverse shock emission provides unique information about the internal structure and composition of gamma-ray burst jets that can't be obtained from forward shock observations alone. High-energy electrons in afterglow shock waves can't maintain their energy indefinitely. They lose energy through radiation and create distinctive features in the afterglow spectrum called spectral breaks. The cooling process affects different electrons at different rates. The highest energy electrons lose energy most rapidly. This creates a characteristic frequency where the afterglow spectrum changes slope. Scientists call this the cooling frequency. Below this frequency, electrons haven't had time to cool significantly. Above this frequency, electron cooling affects the radiation output. The cooling frequency moves to lower energies over time as the shock wave ages. This creates a moving spectral break that astronomers can track to study shock wave evolution. At low frequencies, afterglow material can absorb its own radiation before it escapes into space. This creates an effect called synchrotron self-absorption. The material effectively blocks its own light from reaching observers. Picture a fog so dense that car headlights can't penetrate through it. In afterglows, the radio-emitting material becomes optically thick to its own radio waves. This self-absorption creates another spectral break, but at much lower frequencies than the cooling break. Below the self-absorption frequency, the afterglow appears much dimmer than it would without this effect. The self-absorption frequency depends on both the density of emitting material and the strength of magnetic fields in the shock wave. Scientists can use this information to probe afterglow physical conditions. Radio telescopes sometimes observe afterglows that twinkle like stars seen through Earth's atmosphere. This cosmic twinkling, called scintillation, results from radio waves passing through irregularities in interstellar space. The interstellar medium contains density variations that act like cosmic lenses. These irregularities focus and defocus radio waves as they travel toward Earth, causing brightness variations. Scintillation provides a powerful tool for measuring afterglow sizes. Only very compact sources twinkle strongly. Extended sources don't show scintillation because the twinkling averages out across their larger areas. By monitoring scintillation patterns over time, astronomers can watch afterglows expand and determine their physical sizes even though they're too small and distant to resolve directly. Some long gamma-ray burst afterglows show unexpected brightness increases weeks after the initial explosion. These late-time bumps result from underlying supernova explosions finally becoming visible. The supernova and gamma-ray burst often occur simultaneously, but the supernova light takes longer to become prominent. Initially, the bright afterglow overwhelms the supernova emission. As the afterglow fades according to its power law, the more slowly declining supernova light becomes increasingly noticeable. This creates a characteristic bump in the optical light curve. The supernova bump confirms that some gamma-ray bursts indeed accompany the deaths of massive stars. It provides direct evidence linking burst production to stellar core collapse. Afterglow shock waves create highly organized magnetic fields that align particles in specific directions. This alignment affects how the emitted light vibrates as it travels through space. Scientists can detect this organization by measuring light polarization. Polarized light vibrates preferentially in one direction rather than randomly. The amount of polarization reveals how organized the magnetic fields are. Different wavelengths often show different polarization levels. This wavelength dependence provides information about magnetic field structure at different locations within the shock wave. Polarization measurements represent one of the few ways to probe magnetic fields in cosmic explosions. These observations help scientists understand how shock waves generate and organize magnetic energy. The galaxies that host gamma-ray bursts provide crucial context about the environments where these explosions occur. Deep telescope observations can study these distant host galaxies in detail. Host galaxy observations reveal star formation rates, chemical compositions, and stellar populations. This information helps scientists understand what types of stellar environments favor gamma-ray burst production. Many host galaxies show signs of active star formation and relatively low heavy element abundances. This matches theoretical predictions about the stellar conditions needed for burst formation. By studying dozens of host galaxies, astronomers have assembled a statistical picture of where gamma-ray bursts prefer to occur. This population study guides theories about burst progenitor stars and formation mechanisms. High-energy gamma rays striking Earth's atmosphere trigger a catastrophic chain reaction. The radiation breaks apart nitrogen molecules in the upper atmosphere. These fragments immediately combine with oxygen to form nitrogen oxides. These chemical compounds act like atmospheric poison that devours ozone molecules. Ozone normally forms a protective layer around our planet. This invisible shield absorbs harmful ultraviolet radiation from the sun. Without adequate ozone protection, deadly UV rays reach Earth's surface at levels that can sterilize entire ecosystems. The chemical destruction happens rapidly once gamma rays arrive. Within hours of a nearby gamma-ray burst, significant portions of the ozone layer could disappear. The damage would persist for years while the atmosphere slowly repairs itself. This atmospheric vulnerability represents one of the most serious threats that cosmic explosions pose to planetary life. A single nearby gamma-ray burst could compromise the chemical systems that make Earth's surface habitable. Earth has experienced several mysterious mass extinction events throughout its history. Scientists have struggled to explain some of these ancient catastrophes. Gamma-ray bursts provide a possible explanation for extinctions that lack obvious earthly causes. The Ordovician extinction occurred roughly 450 million years ago. It eliminated about 85% of marine species without leaving clear evidence of volcanic activity or asteroid impacts. The timing and geographic patterns match what scientists would expect from a nearby cosmic explosion. Gamma-ray bursts could explain why some extinctions affected certain types of life more severely than others. Marine ecosystems would suffer first from increased UV radiation. Land-based life might face secondary effects from atmospheric chemistry changes. This cosmic connection suggests that life on Earth faces periodic threats from exploding stars in our galactic neighborhood. These space-based catastrophes could be more common throughout Earth's history than previously recognized. When ozone levels drop dramatically, the amount of ultraviolet radiation reaching Earth's surface increases to lethal levels. UV radiation damages the DNA molecules that carry genetic information in all living organisms. Living cells have evolved repair mechanisms to fix small amounts of UV damage. But these biological repair systems become overwhelmed when radiation levels increase suddenly. DNA damage accumulates faster than cells can repair it. Plants face particular vulnerability because they cannot seek shelter from increased UV exposure. Crop failures could trigger global food shortages. Forest ecosystems might collapse as trees suffer widespread genetic damage. The UV surge would persist for years after the initial gamma-ray burst. Even organisms that survive the initial radiation's spike could face long-term genetic damage that affects future generations. Gamma-ray bursts don't just destroy ozone molecules. They fundamentally alter atmospheric chemistry by creating new compounds that don't normally exist in large quantities. Nitrogen dioxide formation turns the sky brown and reduces photosynthesis efficiency. These newly formed nitrogen compounds eventually fall to Earth as acid precipitation. The chemical rain would acidify soils and water systems. Ocean chemistry could shift enough to dissolve the shells of marine organisms. The atmospheric changes would also affect global climate patterns. Brown nitrogen dioxide absorbs sunlight differently than normal atmospheric gases. This could trigger cooling effects similar to those caused by major volcanic eruptions. Recovery from atmospheric chemical disruption could take decades or centuries. The time scales involved would far exceed the adaptation abilities of most species currently living on Earth. Not all gamma-ray bursts pose equal threats to Earth. The danger level depends critically on how far away the explosion occurs. Scientists have calculated the minimum safe distance for our planet's continued habitability. Gamma-ray bursts would need to occur within roughly 6,000 light-years of Earth to cause significant atmospheric damage. This represents a relatively small volume of space compared to our entire galaxy. Beyond this critical distance, Earth's atmosphere can absorb the incoming gamma rays without suffering catastrophic ozone depletion. The radiation spreads out over such large areas that its intensity drops below dangerous levels. Distance provides Earth's primary protection against cosmic explosions. The vast scale of galactic space ensures that most gamma-ray bursts occur too far away to threaten our atmospheric chemistry. Earth's location within the Milky Way provides natural protection against gamma-ray bursts. Our solar system sits within the galactic disk rather than above or below it. This positioning offers crucial shielding from cosmic explosions. Most gamma-ray bursts occur in regions where massive stars form and die rapidly. These stellar nurseries typically exist in the outer parts of galactic disks or in irregular galaxies with active star formation. Our galaxy's structure concentrates cosmic dust and gas in the disk where we live. This material helps absorb gamma rays from distant explosions before they reach dangerous intensity levels. The galactic disk acts like a cosmic fortress wall that protects interior regions from the most violent stellar death events. Our safe location within this structure may be one reason complex life evolved successfully on Earth. Plants form the foundation of virtually every food chain on Earth. Increased UV radiation would severely damage the photosynthetic machinery that converts sunlight into biological energy. This would trigger ecosystem collapse, starting with primary producers. Chlorophyll molecules that capture light energy are particularly vulnerable to UV damage. When these essential compounds break down faster than plants can replace them, photosynthesis becomes inefficient or stops entirely. Crop failures would begin within weeks of a nearby gamma-ray burst. Wild plant communities would follow similar patterns. Forests might turn brown as leaves lose their ability to process sunlight effectively. The collapse of plant-based food production would cascade through every level of biological organization. Herbivores would starve first, followed by carnivores, leading to complete ecosystem breakdown across large portions of the planet. Ocean ecosystems face particularly severe threats from gamma-ray burst effects. Microscopic marine plants called phytoplankton form the base of oceanic food webs. These tiny organisms live near the surface where UV radiation damage would be most severe. Phytoplankton destruction would eliminate the primary food source for countless marine species. Fish populations would crash as their food supply disappears. This would affect human societies that depend on ocean resources for protein. Marine ecosystems also play crucial roles in global oxygen production. Phytoplankton generate roughly half the oxygen in Earth's atmosphere through photosynthesis. Their destruction would gradually reduce atmospheric oxygen levels. Ocean acidification from atmospheric chemistry changes would compound the UV damage problems. Marine organisms with shells or skeletons would face dissolving habitat conditions alongside increased radiation exposure. Periodic cosmic catastrophes might actually accelerate evolutionary change rather than simply destroying life. Sudden environmental challenges force surviving species to adapt rapidly or face extinction. Mass extinction events create ecological vacancies that surviving species can exploit. This opens new evolutionary pathways that might not exist under stable conditions. Rapid diversification often follows major extinction events. Genetic damage from increased UV radiation could increase mutation rates in surviving populations. While most mutations prove harmful, some might provide advantages for coping with changed environmental conditions. The evolutionary pressure from cosmic explosions could help explain why life on Earth shows such remarkable diversity and adaptability. Regular challenges from space might drive the innovation that makes life so resilient. Modern space-based telescopes provide unprecedented ability to detect gamma-ray bursts as they occur throughout the universe. Satellites like Swift and Fermi can pinpoint burst locations within seconds of their initial flash. Scientists are developing models to predict which stellar systems pose potential threats to Earth. By monitoring massive stars in our galactic neighborhood, they might identify future gamma-ray burst candidates before they explode. Early warning systems could provide years or decades of advance notice for nearby cosmic threats. This would allow human civilization to prepare protective measures or develop atmospheric shielding technologies. Future space-based monitoring networks might track potential threats with enough precision to predict not just when explosions will occur, but also whether their jets will point toward Earth's location in space.